with absolutely, can't think of the word, we'll just move on straight into Mr. Rintoul's bananas for scale. Thank you very much. Oh, Tom.
Thank you, that'll be helpful. Evening everyone, my name is Thomas Rintoul. I am a PhD student here at Cardiff Uni and I work on galaxies. And today I'm going to tell you a bit about one of the biggest challenges in galaxy evolution with this talk titled Bananas for Scale. So, first off, what is a galaxy? Most of us probably think of something like this when we think of a galaxy, this spiral arms with gas, dust, maybe a bar. Our galaxy, the Milky Way, is a spiral galaxy, not too dissimilar to this, but with not quite a strong bar. I'll show you one more like it later. But galaxies take all shapes and sizes. You've got your elliptical galaxies, which are typically much larger, they're much redder, they don't really form stars anymore. But then you've also got your weirder ones like your lenticular galaxies and your ones that are actively doing things, like your galaxy mergers. So you get two galaxies smashing into each other or doing very close flybys. And you get these real long tidal tails off the side of these galaxies as they get ripped apart by each other. And then you've got weird stuff like this thing. We're still not 100% sure how this happened. This is called Hogg's object. It's a ring galaxy, and if you look right through the ring of Hogg's object, there is another ring galaxy right through the back there. They're very rare, but we got two in one picture. And we know about all of these galaxies and more thanks to many, many telescopes around the world that cover every continent. They're in space as well, and they cover every part of the electromagnetic spectrum and even things like gravitational waves. And we want to cover the whole EM spectrum because things look different depending on the wavelength of light that you're looking at. For example, the Milky Way's plane in radio light looks like this. You've got this really bright emission across the plane of the Milky Way and those arcs above and below the galaxy from gas and dust emission. If you move shorter into, say, the infrared, you've then got all of that structure from dust. And if you look dust down the bottom right there, you've got these two little dots. Those are the Large and Small Magellanic Clouds. They are satellite galaxies around the Milky Way. If we look at the visible light, you see all these dark features from interstellar dust that block out loads of the light trying to reach us from the middle of the Milky Way. It's why we look at things other than visible light. And you've got the LMC and the SMC looking a little bit more like galaxies in visible light. You can go shorter still into X-rays. Great for looking inside us if we've had a fall, but also good for finding really high energy objects like supernova remnants or black holes or accretion disks spewing a load of heat out of them. And shorter still into your really high energy gamma rays that might cause us problems here on Earth, but also let us find some of the most exotic and weird things happening in space. Because objects look really different in these different wavelengths, just for another comparison with some galaxies other than our own, this is a galaxy group called Stephan's Quintet. On the left, we have a visible light image from the Hubble Space Telescope, and on the right, an infrared image from the James Webb Space Telescope. And you see in the Hubble image, you've got this blue light on the galaxy on the left there. It's got a lot of young stars, a lot of active star formation happening there. But on the right, you can see through some of that dust and start to see the structure of what's going on inside the disk, not just all of that young star emission. Now, all of these telescopes and all of these observations, we've got thousands and thousands of observations of many, many galaxies. And this produces a lot of data. So, to give a little bit of context, let's talk about this unit called the petabyte. This is 1 million terabytes. A terabyte you're probably fairly familiar with. You'll have had a hard drive of 1 terabyte at some point. Here are just a few sort of observations with galaxies. Up on the left, you'll see the fuzzy orange donuts from a few years ago, the supermassive black hole at the center of M87. That single image came from 5 petabytes of data from radio telescopes around the world. 5 million terabytes. The Gaia mission at the bottom there, mapping stars in our local area of the galaxy, that's done 1 petabyte over about 10 years. And Vera Rubin Observatory, up in the top right, that's down in Chile, and it's doing about 20 terabytes a night, so that means about 60 terabytes over the next 10 years. It's a lot of data. But we have one problem in astronomy, it's time. It's always time. The universe expands, well, moves very, very slowly. It's been expanding for some 13.8 billion years. And for us in astronomy, fast is normally 100,000 years, not like 20 minutes. So that causes us some problems. Because we can only really get snapshots of objects. We can get snapshots of many objects, and for galaxies that means taking images of thousands of galaxies from your very young, very blue galaxies still forming stars, right over to your red and dead elliptical galaxies that don't really do stars anymore. And from all of these snapshots, we piece together what we think happens as galaxies evolve. Because unfortunately, we can't study one object and wait for it to change. Unless we can. Over the last 30 years or so, we've got a lot better at simulating our universe, and simulating galaxies in particular. These are just a few of the simulations from the last 30 years. The Millennium simulation that was done just after the year 2000, through simulations called Eagle, Illustrious TNG, and Colibri, which came out like 2 months ago, so very, very current. This is a video from one of these simulations called Illustrious TNG 300. And what you're seeing here is galaxies start to form from the filaments of the cosmic web. They're all flying past each other, they're merging, they're building up these really bright spots that you can see. Those are the forming galaxy clusters, some of the largest and most massive constructs in our universe. And with simulations like this and smaller ones, we've been able to study galaxies and get a much better idea of how physical processes affect how galaxies evolve. Not just how do they evolve, but why do they evolve in that way. We've been able to study what happens when galaxies merge, when they hit each other and what comes out of that, and what happens when you throw a huge amount of gas into the supermassive black hole at the centre, and it has some significant effects to the surroundings that we will come back to. And this is great. We've got all these simulations. They should tell us loads about our universe. Job done, right? It's a little bit more complicated than that. This is the area that I work in. I work on the gas around galaxies. So not the disk, not the stars and everything around it, where the gas comes from. And these simulations are great. They look really good. These are plots from my first paper. But they have one huge limitation, and that limitation is scale. Scale is a very large problem in studying galaxies, because a galaxy is not just one object. It's an island in the universe of stars, gas, dust, black holes, dark matter. Galaxies are affected by every scale imaginable, from the atomic scale all the way up to the large scale structure of the cosmic web. So for the rest of this talk, I'm going to go through all of those scales, why they matter, and then why that causes us a problem, and how we try and get around that. And we're going to start there with the galaxy disk. Now, this is a galaxy that looks a lot more like our own than the one I showed at the start. A lot more spiral arms, a lot more symmetric. A weak bar, nothing too much. And the galaxy disk is rather big. It's 87,000 light years across, give or take. I thought, well, we could put a banana scale on there, but it's a little bit hard to see, so here is 5 sextillion bananas. We're going to use this as our baseline. So we're going to step down from our galaxy disk, which is full of stars and gas and dust. We're going to go down towards the individual stars. Stars much like our own sun, much larger and much smaller, lighting up our universe. The larger ones, they produce a load of really high energy radiation, and that's going to strip electrons off gas between those stars, creating these lovely things called H2 regions. So that's outside of galaxies, I think, are some of the prettiest images we get. And through various processes where they kick a load of gas out of the galaxy, we get wonderful outflows like we see in the M82 galaxy and others like it. But this is pretty close to us on intergalactic scales, so this is kind of the poster child for the field. And all of this stuff happens because when stars much larger than the sun die, they do so rather spectacularly in what we call a supernova explosion. This is an artist's impression. We don't actually have a recording of this. They're a bit far away. But all of these processes, all your stellar winds, all your supernova explosions, they drive the structure of the interstellar medium. Where those clouds are, where the dense regions are, where the voids in the interstellar medium all are. And the structure of your interstellar medium determines what your galaxy is going to look like. Are you going to have a load of stars forming really close together and then blowing more holes in your galaxy disk? Are they going to be a bit more distributed? Are you going to have many stars forming at all? And all of this structure happens on scales maybe 100 times smaller than your galaxy disk itself. But let's go even smaller. Down to the scale of a star cluster. Now, stars don't form in isolation typically. Ours is a little more isolated, a lot form with neighbours. They form from individual, very large gas clouds. They start to collapse down, and they fragment into many, many different pieces. And all these stars are obviously about the same age. And when you've got a load of very massive stars, the ones likely to explode in a supernova explosion, they're all going to do that at about the same time. So they're going to heat up all their surroundings, and they're going to send a load of gas up out of the disk, but I am getting ahead of myself. These supernova explosions in these stellar clusters are what drives that structure in the ISM. And they can kind of mess up your gas flows in your galaxy. But if you want to mess up the gas flows in your galaxy even more, then, well, let's have a look at a supermassive black hole. This one is ours, Sagittarius A star. It's about 2 million solar masses at the centre of our galaxy, and this is another one of these images that took about 5 petabytes of data to get. Supermassive black holes, when you chuck a load of gas into their immediate surroundings, it doesn't just plop in. We don't all get just like, it doesn't just get swallowed up like a big hoover, because black holes don't really do that. What they end up doing is they end up in a disk around the supermassive black hole. And as all this gas moves around, it all brushes up against each other, gets very hot, friction basically takes over, and emits a lot of light. It's pretty much the most efficient engine in the universe, turning gravitational potential energy into light. And when that happens, it likes to basically blast a load of energy. It heats up its immediate surroundings, it whips up magnetic fields, and it can eject a huge amount of gas into the surrounding space well beyond the galaxy disk. We will get back to that a little bit later. These accretion disks around these supermassive black holes, they're maybe 1,000 times larger than our sun, 100,000 times smaller than the galaxy disk. We can go smaller, past the scale of individual star systems, past the scale of individual stars. And eventually you get all the way down to the separation between individual atoms and grains of dust in the interstellar medium, which are approximately 1 banana apart. It's about 20 centimeters, which I think would be approximately a banana. And this sort of spacing matters because it affects how light moves through your galaxy. It determines, depending on the wavelength of light and the exact spacing and size of your dust grains and your atoms. Is your light going to get scattered? Is it going to get sent somewhere else? Is it going to be absorbed by that gas and dust and heat up that bit of space? Or is it going to do that and then be re-emitted at a much longer wavelength? About half of the light emitted in our galaxy gets absorbed and then re-emitted at a longer wavelength. Or it might just sail right through. It all depends on that play between dust grain size, atomic spacing, and wavelength. So we've got down to pretty much the smallest scales that matter for a galaxy. So we've got down all the way to the atomic spacing, 1 banana between hydrogen atoms. We go back up past stars, past solar systems, past your supermassive black holes, past your star clusters, through the structure of the interstellar medium, and you eventually arrive back at the galaxy disk. Sounds good, right? That's everything, yeah? It's a little bit more than that, because your galaxies, they don't exist in isolation. We'll need to look bigger, see where these galaxies came from and what affects how they are evolving long term. Stepping above the size of your galaxy disk, 100 times larger, you've then got the circumgalactic medium, and this is what I talk about. This is what I research day to day. The circumgalactic medium is very, very underdense. It's less dense than the interstellar medium. The spacing between hydrogen atoms in the circumgalactic medium is 5 bananas. It's about a meter. And the CGM, I'm biased. I think it's really, really important, but a lot of people overlook it because it's rather difficult to see. This is a galaxy group, not too different from, say, Stephan's quintet, and you can't really see it. It's so underdense, it doesn't really emit light. It's very hot, but it doesn't really do particularly much for us trying to detect it with our telescopes. We know it's there because we see how it blocks the light from background sources, but it's not enough to see in an image like this. But the circumgalactic medium is really important for the overall evolution of your galaxy, because it's the source of fuel. Stars don't form from nothing, they form from gas. And they need to get that gas from somewhere. And for the vast majority of galaxies, they get that gas from the circumgalactic medium. They accrete it, it goes onto the galaxy disk and forms stars. If you don't have a circumgalactic medium, if you've lost it through some sort of process, like it being ripped off by another galaxy passing by, you're going to have about half as many stars form in your galaxy. But let's think a little bit larger. going to 100 times the disk, let's go to 1,000 to 10,000 times the size of the disk with a galaxy cluster. These are the largest assemblies of galaxies in our universe. They form, they form at the nodes of the cosmic web, which we'll get to in a moment, and they are full of many, many, many galaxies. Galaxies that fly past each other, that collide, and we talked about galaxy mergers a little bit earlier. Clusters are where galaxy mergers love to happen all the time. But clusters aren't empty. We've seen there's gas around galaxies. There is gas in a galaxy cluster as well. And if that is strong enough, if that is dense enough, and your galaxy is moving through it fast enough, you form these things called jellyfish galaxies, where gas gets removed from the galaxy itself and forms a tail. I like bringing these up because I did a paper on this sort of thing. Galaxies interacting with the gas, with each other. All this happens on the cluster scales and affects the long-term evolution of your galaxy. And all of these things, galaxies and galaxy clusters, all exist within the large-scale structure of the cosmic web, these filaments of gas and dust and dark matter that galaxies form in and flow along and merge into these clusters at the nodes of the cosmic web. So that's the whole thing, from banana scale all the way up to the large-scale structure of the cosmic web. This is the problem that we have. This is a ridiculous amount of scale. For those of us in, we call this an order of magnitude, so we go 10 times larger. So 1 meter to 10 meter, that's an order of magnitude larger. The difference between the banana and the large-scale structure of the cosmic web is 30 orders of magnitude. So times it by 10, and then 10 again, and keep going until you've done that 30 times. That's the difference in scale that we're looking at here. And that's the problem that we have. Because our simulations are great, they've given us loads of information about how galaxies evolve. But they look a bit fuzzy. See, this is a galaxy from a simulation like TNG 300 that I showed you at the start. And each of those dots of light, those star particles, they're a little bit too big, because each of those is about 1 million times the mass of the sun. So not one star, more like an entire star cluster. And this is the problem we have in simulations like this. They do cosmic web really well, but they don't do the inside the galaxy particularly well. We can't resolve all of that structure. We can try and do a little bit better. We can take a simulated galaxy from one of these big lower resolution boxes, and we can run it again at much higher resolution. This one on the right is from a simulation called Auriga. This is from Eagle, and in the Auriga simulation, we've got maybe 100 times better. But that means each star particle there's a lot more of them, but they're still 1,000 times the mass of the sun. We can keep going. We can look at your dwarf galaxies and get down to about 4 times the mass of the sun, which is a lot better. You can get a lot more detail there, but it's hideously expensive to do. We can get, for this simulation, you've got down to this 4 solar mass resolution, we've only done it for the smallest galaxies, something 100 times less massive than our own. And we've done it for that one galaxy, and that's pretty much all we have done it for. Because unlike in the world of AI, people don't really want to give us just unlimited compute time, because, I don't know, money should go to other things, I guess. So we have to make do. What we do is we take the things we do really well. We take our gravity, we take our fluids, we take how the gas moves and all that sort of thing. So we do that really well on our largest scales. And then we take the stuff we've learned from other places, from observing galaxies, observing stars, observing gas around black holes, and from other really, really high resolution simulations that don't try and do the entire universe, they just try and do like one little box of the universe. We take all of the stuff we've learned there, all of our models, our recipes for physics, and we code all of those into our models. We cram them all in, and we let our simulation run, and it gives us a more realistic galaxy. To give you an example, let's talk about those supernova explosions I mentioned earlier. What happens when a massive star dies? I've said we can't resolve an individual star very easily, but we know roughly how much energy we should get from one of these. So we know how many we should get, how many of these supernova we should get for, say, 1,000 stars. So we could say, right, we want that much energy to come out of the star particle over a certain period of time. We can model the effect without modeling the individual thing. Looking again to the supermassive black holes, it's the same idea. We know how much energy we expect to get out of that bit of space when we chuck a certain amount of gas in. So we can't model this thing in detail, but we can model its effect. And we call these models subgrid models. They happen below the resolution, the grid of our simulations. And these models are getting better all the time. The simulation image on the right here is from another one of these Auriga galaxies. And this is showing the temperature of the gas. The blue is the coldest that the gas can get in that simulation, gets to 10 to the 4 Kelvin, which is about 10,000 degrees Celsius. For context, the interstellar medium is actually more like 10 Kelvin, which is minus 260 odd. So we're not getting quite there. Everything in that galaxy disk is happening because of a recipe, a physical model that we put into the galaxy, that we put into the simulation to get galaxies that look reasonable. The one on the left is from this new simulation I mentioned earlier called Colibri, which means hummingbird. It gets a lot lower. In this image, they get down to 10 to the 2 Kelvin, which is 100 Kelvin, or about minus 170 odd degrees. That is not as low as the simulation goes. This one gets down to that 10 Kelvin limit. So it's one of the first ones that's been able to do that. So our models are getting better every day. It's still a subgrid model. It's not doing everything 100% accurately, but we are getting there. We're getting better all the time. So we've covered everything from the scale of banana separating hydrogen atoms all the way to the cosmic web. I hope you have a bit more appreciation for why scale really matters in astronomy, for galaxies in particular, and we'll probably agree that me and my colleagues have our work a little bit cut out for us. Thank you, and I will take any questions. There are questions I can't see because the lights are off. Yeah, but
Just out of interest, in TNG project, what does TNG stand for?
yeah, it's a bit of a Star Trek joke because it is illustrious to the next generation, as far as I'm aware. So it's a bit of a Star Trek joke there. There is another bit of astronomy software called DS9 because astronomy's full of Star Trek nerds. Anyone else? Yeah.
The banana taken for scale, was that an average banana length or a specific banana?
I kind of just thought, it's about 20 centimeters, that'll do.
Respectable, thank you.
Yeah.
With M82, the cigar galaxy, I thought a lot of that material is being pulled out by Bode's galaxy next to it, or is that part of it?
People argue about how much is being removed from M82 and by what methods. The stellar outflow people maintain it's mostly stellar outflows, but the people who look at galaxy dynamics and flybys are a bit more. They think it's a bit more that sort of thing. It's probably a combination of the two.
Fair.
Nothing is ever as simple as we would like it to be. Cool. Thank you for listening, and I'll pass you back.